In this problem, we will use the principle of conservation of momentum to solve the following problem. A railroad car with a mass of 15,000 kilograms sits at rest on the tracks. A second car with a mass of 25,000 kilograms travels down the track at 2.6 meters per second toward the first car. They collide, link up, and head down the track together. And we're asked a number of questions about this situation. What is the momentum of each car before the collision? What is the velocity of the linked cars after the collision? And then we are asked to use kinetic energy to decide if this is an elastic or inelastic collision. Alright, so the first step in the problem-solving process is always to write out the data that we are given. In this situation, a diagram is very appropriate. So we draw two diagrams here, one showing the situation before the collision, and the other showing the situation after the collision. And on this diagram, we have the masses of the two cars. We say that the velocity of car number 1 before the collision is 0, and the velocity of car number 2 before the collision is 2.6 meters per second. Notice that I'm using two subscripts here. The first subscript tells us which car, 1 or 2, and the second subscript tells us when the data are being gathered, before the collision or after the collision, B or A. So we summarize the data that we're given up here. The second part of the problem-solving process is to figure out what we are being asked for. Well, we're being asked for the momentum of each car before the collision, and we are also being asked for their common velocity after the collision. So we'll put that on our diagram as well. We'll draw a diagram showing the two cars traveling together after the collision, and the velocity of car 1 after the collision is the same as the velocity of car 2 after the collision because they are linked together, and we will simply call this a common velocity after the collision, VA. All right, so first we are asked, what is the momentum of each car before the collision? Well, we can consult the formula for momentum as mass times velocity. So the velocity of car 1 before the collision is the mass of car 1 times the velocity of car 1 before the collision, but since the car is stationary before the collision, that momentum is going to be 0. Right, then the momentum of car 2 before the collision is the mass of car 2 times the velocity of car 2 before the collision. The mass of car 2 is 25,000 kilograms, and the velocity of car 2 before the collision is 2.6 meters per second, and that comes out to 65,000 kilogram meters per second. Notice the unusual units for momentum. So this is the momentum of each car before the collision. Moving on to the second question, to find their common velocity after the collision, we take advantage of the principle of conservation of momentum, which says that the total momentum before the collision equals the total momentum after the collision. Momentum is conserved. It cannot be created or destroyed. So the total momentum of both cars put together before the collision has to equal the total momentum of both cars put together after the collision. Well, that total momentum before is P1 before plus P2 before. So that's 0 plus 65,000 for a total of 65,000 kilogram meters per second before the collision. The total momentum after is going to be M1 V1 after plus M2 V2 after. Well, we realize that they have a common velocity after, so we can dispense with one of our subscripts. Factoring out of VA, we get that 65,000 equals M1, 15,000, plus M2, 25,000, multiplied by the common velocity. Well, we add 15,000 and 25,000 together, we get 40,000, and that gives us a velocity after the collision of 1.63 meters per second. The problem has two significant figures, so we would report this as 1.6 meters per second. But we're going to keep the extra significant figure for the purposes of future calculations. Now, as a check, we can calculate the total momentum after the collision for car number 1. That's going to be M1 times this common velocity. That's 15,000 times 1.63. And that means the total momentum after is about 24,000 kilogram meters per second. So the first car, which was stationary before with zero momentum, has gained a little bit over 24,000 kilogram meters per second of momentum. We calculate the momentum of car 2 after the collision. Well, that's M2 times the common velocity, 25,000 times 1.63, and that gives us a after momentum for car 2 of 40,750 kilogram meters per second. So, car number 1 gained a little bit over 24,000 kilogram meters per second, where car number 2 lost a little bit over 24,000 kilogram meters per second. Any discrepancies are simply due to rounding error. Now we move on to the final part, which is to compare kinetic energies. So we first look at the kinetic energy of object 1 before. That will be 1/2 times the mass of object 1 times the velocity of object 1 before. But again, since object 1 is stationary, that kinetic energy will be 0. For object 2, the kinetic energy before is going to be 1/2 times the mass of number 2 times the velocity of number 2 before squared. That's 1/2 times 25,000 times 2.6 squared. So the kinetic energy of number 2 before the collision is going to be 84,500 joules. So adding the two together, there's a total of 84,500 joules of kinetic energy in the system. If this is an elastic collision, that kinetic energy will be conserved in addition to momentum. So the total kinetic energy before will be equal to the total kinetic energy after. If it is an inelastic collision, those two kinetic energy values before and after will be different for the system. So let's see what the kinetic energy of object 1 is after the collision. That's 1/2 times the mass, 15,000 kilograms, times their common velocity afterwards, 1.63 meters per second squared. And after the collision, car number 1 has a kinetic energy of 19,900 joules. So car number 1 gained 19,900 joules in the collision. Looking at the kinetic energy of car number 2, well, that's going to be 1/2 times the mass of car number 2, 25,000 kilograms, times their common velocity afterward, 1.63 meters per second. That comes out to be 33,200 joules. So as we can see, car number 2 lost about 50,000 joules of kinetic energy in this collision. Adding up the kinetic energy for the two, and this comes out to be 19,900 plus 33,200 is about 53,000 joules. So this total of 53,100 joules is significantly less than the total kinetic energy of the system before the collision. About 30,000 joules of kinetic energy was lost during the collision to things like heat and sound and maybe wear and tear on the coupling between the two. The energy could go in a variety of directions, but it is lost to the system. It goes into the environment and is lost to the system. So since some kinetic energy was lost to the external forces, then this collision is an inelastic collision.